Welcome back to the workshop. We want to continue taking a look at differentiation. A nice review. So we talked in our last video that the idea of derivative is based off of the tangent line, or that's how we initially present it. So we looked at a tangent line and found the slope of the tangent line. And essentially what we do is we go ahead and define the derivative to simply be taking away the idea of the graph and what are we left with. So when we consider slope, how we can interpret slope within a context of a problem is a rate of change. So when we remove the graph from our representation, where we remove the representation of graph for a function, and we're just left with the function, what did that slope represent? It represented the rate of change of the function. So a derivative of a function is the rate of change of the function. That's very important because something that you take away from Calc 1 frequently is that a derivative is slope. Yes, it is, but only when you're talking about the graph of a function. And we want to make that distinction here. When we no longer are considering the graph, we're just considering the function. What is the derivative? It's the rate of change of the function. So we want to understand that distinction. We have a particular context within we're talking about graphs, we can talk about slope. When we're not talking about graphs, we're not talking about slope. What are we talking about? Rate of change. Okay, so we want to have an understanding of that. All right, so let's take a look at some notes really quick then. So if we want to talk about the derivative of a function at a point, so we have a particular x value in mind, that x value is a, so the derivative at x equals a could be defined or is defined by the limit as x approaches a of exactly what we wrote down last time, f of x minus f of a divided by x minus a. And the notation for that is f prime of a. Easy enough. There's another way that we could write that, that definition. If I replace x with a plus h and let h go to 0. So x approaching a is the same as h going to 0. Then I get this alternative definition, and I have f of a plus h minus f of a divided by a plus h minus a would just be h. And this alternative definition is what we use when we start talking about the general derivative of a function. So this is the derivative at a specific point. We can then talk about the derivative of a function. Now, again, notationally, this is wonderful. I haven't had to change anything from the slope of a tangent line to the derivative of a function because conceptually, they're the same thing. We're just working within different contexts, right? A graph versus a general function. So notationally, it's the same. We just are interpreting them ever so slightly differently or more generally in this case. This is the general interpretation, derivative. All right, so in general, if I wanted to find a representation for the rate of change at any point, I wouldn't want it to be at some specific value x equals a. I want it to be at x, and then I plug in x. So what I do is I use this alternative definition, and instead of saying at some specific point a, I can now replace this a with an x to let it be some arbitrary point. So I'm looking at an arbitrary point x. So it becomes general derivative becomes f of x plus h minus f of x divided by h. So this is the limit definition of a derivative. These are not the things that we use often. In fact, we will almost never use this in Calc 2, if I remember correctly, but we have to have this understanding of where the derivative came from. That we do need to have. Notations for this, again, f prime of x now instead of f prime of a, because we're looking at the general point x. And there's also the notation of df dx. Now, why are there two different notations? Well, it depends on who you want to focus on when you're talking about the development of calculus. The different notations come from different people. There's Leibniz notation, Newtonian notation, right, our two founders, and then Lagrange, I think, might be the other person. I'm not certain on who gave the third notation. The notation that we don't use for sure would be f dot. So it's really similar to the prime notation. F dot dot would be two derivatives, right? One derivative, two derivatives. So the dot and the prime are essentially the same notation, which is why we don't do the dot notation, just do the prime. But this one is a little bit more powerful because it starts to really focus on the relationship between differentiation and integration, or anti-differentiation. So anyway, definition of derivative, and we're good there. So I'd like to pause again, and in our next video, we'll just take a look at the most basic differentiation rules. If you're familiar with these already, I would say, right, there's a sheet of these in the textbook. So do you have to watch the next video? No. All I'm going to do is write down what each of these rules are. So if you want to skip over the next video, that's fine. Maybe watch it at 2 speed. That's fine too. I'm just going to remind us of what these rules are. So I'll see you guys back in the workshop in just a minute.